Greetings. I am Nitish Mukhopadhyay, professor in the Department of Statistics at the University of Connecticut Stores. Welcome to the series, The Films of Distinguished Statisticians. It is a joint program of Pfizer Global Research and Development, the Department of Statistics at the University of Connecticut Stores, and the American Statistical Association. The funding helps us to bring the most distinguished statistical scientists to our university. It also allows us to film the Pfizer colloquia and conversations for the archives of the American Statistical Association. Before we begin this segment, Conversations with Distinguished Statisticians, in this series, with deep gratitude, let me mention two colleagues, late Professor Harry Poston from the University of Connecticut Stores and Dr. David Salzberg from Pfizer Incorporated. A bit of history. Late Professor Poston and Dr. Salzberg engineered this program some 30 years ago. The first film in this series was launched in 1978. I am especially proud to dedicate a conversation with Professor Emanuel Parzen in memory of Professor Poston. I am delighted that Professor Joe Newton from Texas A&M University, College Station, and Professor Grace Waba from the University of Wisconsin-Madison would participate in a conversation with Professor Parzen about his life and work. Now it is my great pleasure to invite Professor Newton to take over the proceedings. Enjoy.
Hello and welcome to this conversation with Emanuel Parzen. My name is Joe Newton and it's my honor to be Professor of Statistics and Dean of the College of Science at Texas A&M University. With us here is Professor Grace Waba from the University of Wisconsin. Grace is a very distinguished statistician. For example, she's a member of the National Academy of Science. Grace and I have one important thing in common. Namely, we're both PhD students of the subject of our conversation, Manny Parzen. Grace when he was at Stanford, and me when he was at State University of New York at Buffalo. Manny Parzen is widely recognized as an extraordinarily influential person in the development of modern statistics. After bachelor's and doctoral degrees in mathematics at Harvard and Berkeley, Manny spent 15 years at Stanford University, 8 at State University of New York at Buffalo, and the past 28 years as a distinguished professor at Texas A&M University. Perhaps the most remarkable thing about Manny Parzen is that he is widely known in many different areas of science, and different groups of scientists know him for different things. For example, several generations of scientists learned probability and stochastic processes from his very influential texts. Several areas of science and technology have discovered, and sometimes rediscovered, reproducing kernel Hilbert spaces through Manny's seminal work. He is one of the fathers of modern time series analysis, spectral density estimation, and probability density estimation. He's made many other contributions, and the three of us will try to expand on these in this conversation. I'd like to start by asking Manny to talk about his childhood and his family and the period leading up to going to Bronx High School of Science. Manny?
Well, I was born in New York City in Harlem, 102nd Street and near Fifth Avenue. I'm the youngest of 9 children. Mm-hmm. My father was a rabbi, and we came from a family that none of us had gone to college before. They had arrived from Poland in 1920. All my brothers and sisters went to the City College system of New York, and I was lucky to turn 16 in 1945 at graduating from Bronx High School of Science at a time when the Ivy League, in particular Harvard, was interested in increasing the number of students from public high schools. So I and another friend of mine, out of the very bright graduates of the Bronx High School of Science, were admitted to Harvard. And of course, I had a very successful career because I majored in mathematics, because I had entered wanting to major in economics and physics, but because of the large number of students coming into college at that time, they refused to honor the joint major in physics and economics. So it was a halfway house in which I could always go in either direction. I went to mathematics. But at the same time, I was always trying to not do everything the way everybody else did it, so I wrote a bachelor's thesis in probability theory, because obviously probability theory was not the most respectable part of mathematics. That made it attractive to me. Also, probability theory had philosophical aspects. So my thesis was half on the philosophy of probability, the idea of the subjective and objective, and also on the mathematical foundations of probability. So at an early age, I began reading all the textbooks of probability, which I was able to use in writing my own probability book.
Okay. Could you give us just a brief overview of your career and the stops that you've made along the way to get to where you are?
I feel that I've been very, 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 very lucky. When I got my PhD at the University of California, Berkeley Statistical Laboratory, the outside member of my PhD committee, assigned randomly, was a physicist who was about to become director of a physics laboratory at Columbia University on the problems of underwater sound and anti-submarine warfare. So he hired me to be the mathematician for his group of physicists. And that was a very fortunate thing, because it introduced me to all the problems that were emerging in signal processing theory, statistical communication theory, and of course I became aware that there was a problem of spectral analysis. At the same time, I was teaching at Columbia and teaching advanced probability, because I had done my thesis in advanced probability. And one of the students in my advanced probability course was the chairman of the Department of Statistics at Stanford University, who was on sabbatical leave at Columbia. So he hired me to go to Stanford in 1956.
Who was that?
Dr. Albert Bowker, who had a very successful career as chancellor of the City University of New York and the University of California in Berkeley, and was my first department head. But this reminds me of another story that from the beginning of my career, I was very close friends with the people who were my bosses, Dr. Bowker, Dr. Robbins, who was the head of the Department of Statistics at Columbia. And then after 15 years at Columbia in 1970, the year 69-70, I spent in New York City as an IBM fellow at the IBM Systems Research Institute. And while in New York, decided to move to the East because my good friend Marvin Ellen was forming an innovative program at the State University of New York at Buffalo. So in 1970, under Marvin Ellen's invitation, I moved from Stanford, first was at Columbia for 3 years, and at Stanford for 15 years, and I moved to Buffalo for 8 years. And then the exciting group that we had established kind of was not able to be properly supported by the university, so Marvin and his group moved to a very successful career at the Harvard School of Public Health Department of Biostatistics, and Joe Newton and I moved to Texas A&M, where we've been ever since.
Great. Let's talk about the first of the things I mentioned at the beginning of where you're so influential, and that was your 2 textbooks. And what's fascinating to me about that is that these are books that you wrote when you were an assistant professor, which nowadays we don't actually ask assistant professors to do. So how did all that happen?
You have to understand the atmosphere in 1953 when I went to Columbia University. The electrical engineering department at Columbia University was the most advanced, innovative department, and they were leaders in applying probability theory to engineering. And they were spending, each faculty member was spending half of their course teaching probability, which was clearly inefficient. So they felt the need to have a course in probability to be taken by electrical engineering graduate students. And I was there, and I began teaching such a course to hundreds of students who recognized that I was the path of their future. So they were very attentive students. And of course, I wasn't happy with any existing textbooks, so I clearly had to work on the problem of writing a textbook that would be a book on probability, which in my opinion and the reviews say was an unusually rigorous introductory book that would enable engineers to prepare for their profession. So essentially it was a stimulation of the environment in which engineers wanted to learn probability that caused me to write my books on stochastic processes.
So you wrote for engineers.
Oh, I definitely wrote, well, but I wrote for engineers. Let me make a remark about my book. I've met engineers who said, your book purports to be a mathematics book, but I can tell it's an engineering book.
But I know a lot of physicists who learned probability from your book too.
I have physicists who tell me they've solved every problem in the book as a way of learning probability. No, my book is a very rigorous book at the elementary level, rigorous, but it has also many examples, and I have many topics of engineering, signal to noise ratio. I feel there's still many topics that I have in that book of interest to physicists and engineers that are not covered in other books.
Right.
I read that book before I went out to Stanford, before I met you. And when I got to Stanford, I was thrilled to find out that you could be my thesis advisor.
Lucky me.
No, lucky me.
And I read it also and was thrilled to have you as my advisor. But can you, so it was published by Wiley? That must have been exciting for a young assistant professor.
Well, actually, it was even more exciting because Wiley had published the leading book in probability by a fella. And it was a very diplomatically delicate question about publishing my book on probability. Now, they obviously felt there's going to be a book out there competing with fella. What's the difference if they publish it or someone else? And so they had to get very strong evidence from leading probability theorists, Dr. Joe Doob and Mark Katz and others, that this book was worth publishing to avoid the wrath of fella. And so it was a very interesting situation in which they were going very diplomatically, and of course they published the book, and it was immediately just as successful as Fella's book. They doubled overnight the number of probability books they sold.
The Stochastic Processes book, had there ever been a book like that before that?
I think the reviewers said there was the first book at an introductory level. The idea was to really write a book at the calculus level that introduced the really working formulas of the theory of stochastic processes. And I know many engineers, very successful leaders in optics and so on, who told me that they based their whole career on applying my books. And Alice Whittemore told me she read my book for breakfast, lunch, and dinner. It was indispensable reading.
A biostatistician.
Yes.
Well, back to modern probability book for a minute. Can you talk a little bit about, there's a couple chapters at the end that I remember thinking were way beyond what I should be able to learn at the time I was reading the book.
I felt strongly that the first 8 chapters were a introduction to probability. In fact, the first 8 chapters are 2 levels. There's a kind of a just requiring algebra in the first few chapters, and then it moves into calculus. And in an introductory probability course, we covered the first 8 chapters. But having studied advanced probability from the textbook of Loew, which is just being published, I felt, and I had many ideas, many new ways of proving the facts of advanced probability. I took the opportunity to add these 2 chapters, which were a mini course in advanced probability with, I think, very streamlined proofs of many facts, plus many new facts. And I didn't see why it would be a problem to have 2 chapters, because I did feel that the need for a book on advanced probability at an introductory level was what I accomplished in the last 2 chapters. And I also feel that in terms of making me famous, now people said you're very famous in Europe, people have read your probability book. I think what attracted them was the last 2 chapters rather than the first 8
More
chapters.
mathematical, like Loew's book was very mathematical.
And many formulas in there that really were not elsewhere. For example, I used my insight into kernel estimation, and instead of proving the inversion formula for the probability distribution from the characteristic function using the ordinary kernel, the Dirichlet kernel, I proved it in terms of general kernels, which made it a more easy proof to use it to do it for the general K case instead of a specific kernel case.
Right. Next topic, reproducing kernel Hilbert spaces.
Well, of course, that's a very fascinating topic because...
First, can you tell us what a reproducing kernel Hilbert space is?
Let me tell the story, and then I'll tell what a reproducing kernel Hilbert space was. I was a graduate student...
It still is.
Still is. I was a graduate student in Berkeley, where the system of graduate education was, rather than a so-called prelim exam, they would give you a topic, which you would then research and present a lecture on it to your PhD committee. And it would be cryptic words, and no idea of where to find this topic. Just for the sake of the historical record, the topic that I was given of reproducing kernels, I'm told by Percy Diaconis, who's researched the question, had previously been given to Lucien Lecomte, who turned it down, refused to take it.
What a mistake.
So it was given to me, and I was a contemporary student with Lucien Lecomte. And I, of course, found it a fascinating topic and enjoyed learning about it. And then 5 years after I learned about it, that's just as a problem for my PhD, I was very involved in teaching engineers the ideas of statistical communication, which was then being developed by engineers, and realized that I could give a nice streamlined presentation and derivation and generalization of what was then being done, and to extract signals from noise, sinusoids and noise, sine waves and noise, using the formalism of reproducing kernels. Now the idea is that instead of writing your equations and integrals and sums, I used to say to people, when you manipulate large numbers of symbols, you're bound to make a mistake. You can replace all those symbols by a simple notation called an inner product in a space called the Hilbert space, which has inner products. Now the reproducing kernel has a special role among Hilbert spaces, that it consists of functions which have values at a point, and the value of the function at a point t, if we fix the point t, is a continuous function of the function. So it's a linear functional. And that means that you have representation of the value of the function at a point as a linear functional, which is a very powerful technique for applied mathematics when you have it. That's why kernels were developed. They were developed among applied mathematicians in 1920 to provide integral representations of the value of the function at a point. Now that's a purely mathematical idea. It turns out to have a link to statistics and stochastic processes, because the kernel of this space is a so-called non-negative kernel, which is also true of a covariance kernel. What a reproducing kernel is a way of, in the word of physicists, of getting a language to discuss the unknown. You have objects of any kind. They could be random variables or patterns, and you essentially can introduce a measure between these objects by a kernel function, which has the properties of a positive definite kernel. And all kinds of consequences follow from that. And the beginning of that application was my own work of applying kernels, which I learned about mathematically, to the statistical problem of analyzing signals and noise.
Right, so that's why it keeps popping up everywhere, is that these problems appear in all different fields. And Grace, you've used reproducing kernel Hilbert spaces a lot. Can you give a couple of examples?
A lot is like an understatement. My 39 years in the academic world, about 3/4 of the stuff I've done has involved optimization problems in reproducing kernel spaces. The smoothing spline is a special case of an optimization problem in a reproducing kernel space. That was the first thing I did with George Kimmendorf. And now you can go into R and find half a dozen codes that will do a smoothing spline. It's a great way of drawing a smooth curve through data. And they're related to solving ill-posed inverse problems by regularization methods. You can do that in the context of reproducing kernel spaces and get convergence rates and so forth. The thing that statisticians use most is the penalized likelihood estimate, which was in Finbar-O'Sullivan's thesis. It's in O'Sullivan, Yandel, and Rayner, and Jess, I think, around 1986. And the thing is, as Manny pointed out, you can define a positive definite function on all kinds of domains. So your data can be in any kind of domain. It could be an interval of the real line, or a Euclidean D space on the sphere, the atmosphere, and so forth. And more recently, so they weren't really used very much for many years, except for people who like to do penalized likelihood. But a few years back, it came out that the famous support vector machine, which is what computer scientists like to do to classify things, can be written down as an optimization problem in a reproducing kernel Hilbert space. And then once you do that, you can compare it to penalized likelihood, you can compare it to robust smoothing, and all kinds of other things that are well known in the statistics literature. So all of a sudden they become very popular, and I get a lot of computer science students in my class, and it's a lot of fun. Just last week, one of the students gave a talk on reproducing kernels defined on text.
Text.
So phrases, so you parse a sentence and you have that creates some kind of a structure, and then you develop positive definite functions on these structures. And once you do that, then you have a distance measure. And once you have distances between these abstract objects, you can cluster and classify them. So it's got a lot of uses.
I want to get one clarification. I've heard your story about finding a little piece of paper in your mailbox, and did it say reproducing kernels, or did it say reproducing kernel Hilberts?
No, it said reproducing kernels, and there was at that time no literature. The founder of reproducing kernels, Arenstein, had published an obscure paper in French in the Cambridge Philosophical Proceedings, and was about to publish a major paper in Transactions of the American Mathematical Society, which of course I had no reason to look at. I had no clue whatsoever of where to find it. But finally someone said, I think there's a paper in French on the subject. So I read Arenstein's 48 paper, and then I began understanding about the history of the subject. And
and there was no Google at the time.
No,
I was going to say, you couldn't
Google, but there was no hint.
Arenstein.
And you were just handed this little paper in your box. Your topic is kernel, reproducing. The only was two words, reproducing kernels.
Right.
And I had no idea what connection that could possibly have.
Who picked that subject?
Well, Loewe had been a student in Paris with Arenstein. So he knew about reproducing kernels by being a student with the founder. And he had one paragraph in his in a paper in 48 that pointed out that the covariance kernel of a time series and the covariant and the kernel of a reproduced kernel Hilbert space were both non-negative definite kernels. And therefore there's a representation of time series in terms of the kernel space. However, I established a connection with statistics because the probability theorist only has a single probability measure and the representation of the time series. In statistics, we have a time series with an unknown mean value function, and you want to have this isomorphism between all the Hilbert spaces for different mean value functions work. And the condition for that turned out to be that the mean value function belongs to the reproduced kernel Hilbert space. So it actually answered the important question, how would you write a formula to the likelihood functional of a time series as a function of the unknown mean value function? Well, because the mean value function time series is absolutely continuous with respect to the zero mean time series, you have a formula for the likelihood ratio. And once you have the probability density, all of statistical inference flows immediately. So let me give another important idea here. Suppose that you're an engineer and you're working on the problem of detecting a sine wave in noise. And you work with functions and you more or less derive the answer, assuming all possible assumptions that the function you're looking for is analytic and so on. It turns out that the final answer only involves, say, first derivatives. Well, using the structure, reproducing kernels, you can say, forget about how you derive that answer. Now looking at it, that's an inner product defined on differentiable function. So immediately you can conclude that the formula is valid only on the assumption of differentiability, well, although you derived it in your calculations using all the possible assumptions at all with the function f. But the final answer only involves first derivatives. That's the only assumption you need.
So all of this led, in some sense, to time series analysis work and spectral estimation.
Exactly right.
And so...
let's give the scenario.
Yeah, so give the...
well, 1957 or thereabout, I discovered reproducing kernels while lecturing to engineers on telling them what was in their literature, essentially the book by Lanning and Batten, Automatic Control, where they were the leaders in trying to figure out how to estimate signals and noise. Well, that made me decide to be a time series analyst. Well, I already also published extensively on spectral analysis. I had two things I'd done already. Spectral estimation, which arose out of my work at the physics lab, and where I found the optimal kernel of the Parzen window by a theory of optimal rates of convergence. And then the reproducing kernels, which is, so to speak, time domain representations. Well, boy, I should become a time series analyst. And there weren't many time series analysts. It didn't exist, really, time series analysis. At that time, Granada and Rosenblatt were trying to develop the concept that the old fumbling methods of econometrics, of time domain models, autoregressive models, should be replaced by spectral estimation. They were still trying to establish an identity for time series analysis and spectral estimation. There was hardly anybody working in the field. So I essentially said I'm going to become a time series analyst, and it happened to be in England in 1958, and discovered there were a few time series analysts in England, namely Gwilym Jenkins and Maurice Priestley. So I got to know Willem Jenkins very well and invited him to Stanford, and as a result of that, he became friendly with George Box and wrote the books Box and Jenkins on time series analysis. And we also had a small international community of time series analysts, and the interesting story how he got close to Hiro Akayake and Ted Hannon. But essentially, there was a small international community of time series analysts who were very well known among the engineers and very influential among the engineers. And that's how I became a time series
How
analyst.
about Tukey? How was he related?
Well, of course,
to all
I was
this?
very strongly related to Tukey. Tukey had, for Tukey, the problem of spectrum analysis he had started it in response to the need of engineers at Bell Labs. And he always said that his work on spectral estimation, and essentially spectral estimation is the first example of data modeling that modern statisticians are really essential to modern statisticians. But I never felt that there's any, so to speak, crisis in statistics. I started off my career in data modeling using time series analysis and spectral analysis. Now, spectral analysis, Tukey writes, is the motivation for his starting data analysis and his paper of the future of data analysis that I love so much that people should know about, the 1962 paper. And so I knew Tukey, but of course, he had his own brand of spectral analysis, the Tukey window, and I had my brand using the Parzen window. But I should say that my friends among the economists used to say, if you want to publish, use the Parzen window because it gives more interpretable results, especially for coherence. The Parzen window is positive. You don't have, so to speak, negative values to, so to speak, explain. Tukey felt negative values are good. They show you leakage. Well, people don't want to explain things. Let's just get an answer we can publish. So that's what the Parzen window did.
Do you remember the day that you discovered that the kernel that's become known as the Parzen window occurred to you? I mean, was that the result of some calculation or lucky guess?
No, as usual, it's because I had a deadline. In 1957, I was giving an invited talk at the statistics meeting on spectral estimation, and I felt strongly that I wanted a recommendation that I had this theory of optimality, and now let's find an example. Mm-hmm. Now, people always say, oh, well, I see your example. You can do it over here and here. And I said, no. You get into the right ballpark with this example, and once you're in the right ballpark, then the kernel doesn't matter so much as the bandwidth.
Right.
So it's not like, oh, can't I use another kernel? So and the ballpark was, you want a non-negative estimate which had the right order of convergence for optimality. Right. And the existing kernels, the Bartlett kernel and the Tukey kernel, did not obey that criterion, and the Parzen kernel was invented for this talk to obey the criteria that I said we wanted to have for a successful spectral estimator.
Right. So a kernel that has the same properties as the Parzen kernel, that non-negative and various other things, would be okay if you chose the bandwidth, right?
And actually, it's a very interesting story, because writers on the issue of the role of mathematics and statistics often quote the research on choice of kernels in spectral estimation as an example where a lot of mathematics was done that turned out to be unnecessary because the choice of kernel was not important, only the bandwidth counts. But they were wrong, because we needed the research to tell us if you had a kernel of a certain kind, you were okay. Right. But it wasn't like the choice of kernels entirely unnecessary. You had to get the kernel with certain properties. Right. But I am always amused when people try to argue that a lot of people who did mathematics work in statistics were really not helping. I feel that the examples they quote aren't true.
Did spectral estimation or probability density estimation come first?
No, spectral estimation was a problem that arose out of the engineers. It emerged in the Second World War. It became popular at Bell Labs. It caused Tukey to be interested in it. And I took it up, and Grand and Rosenblatt took it up. And just speak of spectral estimation, in 1959, John Tukey, Willem Jenkins, and I published 3 papers in technometrics for an applied audience that I feel were very instrumental in making the topic of spectral estimation a consumer good and widely practiced by engineers and economists. At the same time, there emerged interest in the concept of probability density estimation. And I had all these techniques for spectral density estimation And so I felt that I could write a comprehensive paper on probability density estimation, and in order to have an application of it, I wrote a paper called Estimation of the Probability Density and the Mode. So that turned out to be an interesting problem in its own right. So I had two directions there, estimation of the mode and estimation of the probability density.
Okay. Well, you mentioned Gwilym Jenkins and Box and Jenkins, and that was Box-Jenkins was very influential
Yes.
for a long time, and it's kind of ironic because Jenkins really wasn't he more of a spectral
Yes,
person?
Jenkins was a spectral analyst, but as I said, because he came to visit me in the United States, he also visited George Box, who got him interested in his problems, and essentially what Jenkins pointed out to Box was that the problems of industrial quality control, industrial process control that Box was interested in, they used words like proportional control and differential control and constant control, integral control, anyhow, that the conditions under which these control were appropriate were essentially the time domain models of autoregressive processes, moving average process, and then integrated processes. So there was a clear connection between interpreting the control, the process control, and time series models, and they worked together over many years, working out the details of how to actually, in practice, model time series, and their ultimate motivation was process control and also prediction.
Right.
Now, unfortunately, it created a generation of people who only thought that in the time domain, and we emphasize that there is value in interpreting results, both the spectral domain and the time domain. And the reason why that's true is the following. If you're trying to extract a signal in noise, really the behavior of the spectrum of the noise is what determines the properties of your modeling process. So if someone suggests a model of a certain noise, I might come to the conclusion, I believe your model for the noise has the right spectral shape and therefore it's good. I don't agree with your time domain model. If you want a prediction, I might choose a different time domain model. But for purposes of extraction of signal and noise, it's only the spectral shape of the model that counts. So that's why I think it's important to use both the spectral domain and the time domain.
Right, right. For example, estimating the mean of a time series is a function of a spectral density at 0, and if you don't know that, you get all kinds of tortured-looking formulas for things.
And that turns out to be a very important problem in simulation. People who simulate are estimating the mean, but they want a formula for the variance. Right. So it turns out that they automatically have to use time domain modeling ideas to get a formula for the spectral density at 0, which is the formula for the variance.
Right. Well, I know one of the interesting things about your life has been the people who you have known. We've mentioned some already. Let's do a few others, like David Bellinger.
Well, I've been very fortunate. As I said, the time series community was composed of wonderful, fascinating people, and there weren't too many of us. So we all were very, 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 very close. And in 1961, I spent a year visiting Gwilym Jenkins in London. And at the same time, that year, Herman Chernoff was on leave, David Bellinger was on leave, and actually some engineers whom I later got involved with in organizing a joint stochastic process applied to engineering time series seminar in Tokyo, which resulted in my close friendship with Hiro Kayake. Now, David Bellinger and I just were very, very close friends starting from the year we were together in London. He just got his PhD. He was a postdoc in London, and he's done very seminal work in time series. He's visited us at Texas A&M several times, and we just were very supportive over the period of our career.
Right. Another famous man who recently won a Nobel Prize in economics, Clive Granger.
Well, he and I are very close friends again because we were, from the very beginning of his career, again, in the period I was in England, 61, I visited all the universities. As an American visiting England, I discovered that somehow it was easier for me to go visiting all the universities and become friendly with all the British statisticians than they perhaps were with each other. So I went traveling around and visited Peter Whittle in Manchester and Maurice Priestley in Manchester and Clive Granger in Nottingham. And he was one of the initiators of the applications of spectral analysis to economics and then later of co-integration. And he's still a big fan of statistical methods in economics, in particular more recent work on quantile domain. I just kind of jumping ahead, but in terms of my own career, the issue is traditional statistics models in terms of mean and variance, but now we should start modeling in terms of distributions, and the quantile domain is a good way of modeling distributions. So I think if you look at the modern work in more or less financial time series and time series, there is a movement from the time domain, from the time and mean and variance methods to distribution methods. So I've been involved with Clive Granger as a close friend and supporting each other in our careers in many ways since 1960, and he's now evolved into also being interested in quantiles.
Good. An example of a non-statistician is Thomas Kylath, electrical engineer at Stanford. Maybe he is a statistician?
No. Tom Kylath, again, let me talk about how I met Tom Kylath. In 1959, again, there was a symposium organized by Bellman at UCLA on problems of statistical communication. And I was there, and Tom Kylath was there, and of course I spoke to him about reproducing kernels. I should remark that the engineers, I was told, were very upset by what I said. They said, you can't make claims like that. You said you solved all the problems with this technique. 10 years later, these very people told me you were right. And one of the reasons they said I was right was that Tom Kylath took up the cause and wrote a long series of papers on applications of reproducing kernels to engineering. And he had a student, Weinert, who published a beautiful collection of papers on reproducing kernels applied to signal processing. So again, Tom Kylath was very strongly, of course, as most engineers, they were always confused about the difference between probability and statistics. They understood probability, how that applied to engineering, but they weren't so clear how statistics came in. But nevertheless, he was very active he and his students in the study of the role of reproducing kernels in signal processing theory.
Well, I know he and his group wrote paper after paper on how to compute various things, and I know that computing has always been an important part of
fast algorithms, they call it.
Fast algorithms, yeah. So that was good.
Well, I should point out that the first fast algorithm of time series is the Levinson method of computing. This is a very interesting story because Wiener developed prediction theory, and naturally it was pretty difficult for the engineers to understand until Levinson wrote the appendix that said we can solve the prediction problem recursively by these equations. So I spoke to Levinson about how he discovered that recursive formula, and I pointed out it had nice interpretation in terms of innovations and things like that. He said, no. He just looked at the equations and saw if you took the bottom and took the top, you could go back and forth. So he had written these very successful recursion equations.
Where was he?
At MIT, the same place that Wiener was, where the work on the...
okay.
I should point out that Wiener developed the theory of time series in a famous classified report called the Yellow Peril, the application of time series to prediction. And the engineers, the reason why all the engineers became so passionate about probability, and then I wrote my book for them, was they were trying to understand Wiener.
I see.
Wiener was the impetus for their becoming interested in probability.
Right. And it was classified because it was relevant to the war effort.
That's right.
Yes. Next might be Marvin Ellen. You mentioned him earlier, but he's...
Well, Marvin Ellen, again, I became close friends with Marvin when he was on leave in California in late 1950s. In my book on probability theory, the only person I mentioned in the preface was Marvin, because he took the time to make lots of wonderful comments. So I should point out that I thank others for institutional support, but in terms of direct comments on the book, Marvin was mentioned, and he led me to join him in Buffalo in 1970. And I should point out parenthetically that in order to meet the needs of medical scientists who wanted to conduct clinical trials involving many hospitals, an organization needed that would provide this vehicle for collaboration, which became the Frontier Science and Technology Foundation, which Marvin founded in about 1975, and I was one of the original members of the board of directors, and my contribution was the name Frontier. He called me up and said, I'm about to sign the papers to create this company. What should we call it? And I said, well, we're in the Niagara Frontier, and we're at the frontier of science called Frontier.
Well, I have one more, but I want to wait for later. Say if you want to talk a little bit about conferences that you've organized. I know that there are a number of very seminal references that were the proceedings of conferences that you organized.
Well, I'm very proud of the fact that a conference proceedings on distribution functions by Jim Durbin and a conference proceedings on the quantile functions by Miklos Chogo, both were NSF regional conferences that I organized. I think it's amazing, the coincidence, that the two important topics of distribution functions and quantile functions were both organized by me. In the area of time series, we organized what's called a boot camp for young researchers that the people who attended that for 2 weeks look back upon as a very seminal period in their careers. And unfortunately, we get the energy and the funding to do these things only once, but I think that the idea of that time series boot camp is a very good model for how to help develop young researchers. There was a conference we organized at Texas A&M on time series analysis of irregularly spaced data, which again is a very important problem that has had a lot of references. In 1990, there was a one-month conference at the Institute of Mathematics at the University of Minnesota that brought together all the different streams in time series analysis, spectral domain, engineering, economics, and so on, for 1 month of conference at the University of Minnesota. And
How about your relationship with Japan? That's been very important.
Well, Japan is a very interesting story. What happened was, in 1960, the U.S. and Japan signed a treaty to have U.S.-Japan joint seminars. And NSF was interested in establishing contact between the U.S. and Japan. So they asked an engineer, who happened to be one of the engineers I met in London when I was a year there, to figure out how to organize this conference. And he had read a review I'd written of the work of Akayaki, and he contacted Akayaki, who essentially said, well, I'm too junior, but he more or less created the contacts to form a U.S.-Japan seminar application of stochastic process engineering in Tokyo in 1965, where there were 11 engineers and one statistician from the Japanese side, and 11 engineers and one statistician from the American side, and we spent 1 week together, night and day, knowing each other and discussing the methods and so on. And I became very, very close friends with Hiro Akayaki and invited him to the United States. And we organized 2 more U.S.-Japan joint seminars on time series analysis, one in Tokyo, one in Honolulu. And I should point out that when Hiro developed his AIC criterion, I said, gee, I need a criterion too. So I felt impelled to develop the CAT criterion for determining the order of an autoregressive model to fit to a time series.
Which is interesting that asymptotically they're very similar.
They're very
right?
similar.
And what are they for?
Well, one of the interesting problems of analyzing time series and spectral estimation is you can use what's called the direct, well, now, without naming names, the one method we first discovered was in terms of the kernel, like the Parzen window. Another method is to develop a transformation to white noise, a whitening filter, and take the spectrum of that transfer function as the estimated of the spectrum of the time series. The problem in spectral estimation is choice of bandwidth. When you use the kernel method, you have to choose a bandwidth. Well, if you go the time domain route of using an approximating autoregressive scheme, the equivalent problem is determining the order of the autoregressive scheme. So we have a criterion which we graph and whose minimum is the order at which we determine, we say, the best fitting autoregressive scheme. So that's the order of the autoregressive scheme which we use to form the, so the unknown, see the big problem, let me make a remark. The problem of autoregressive spectral estimation is also called maximum entropy method. And it's often described by Bayesians as an example of the triumph of their approach. But that doesn't really solve the problem of the Bayesian approach says you want to, or maximum entropy says you want to find the answer subject to the constraints of this information. It doesn't solve the problem of what information you should choose, in particular how many lags, what the order of the autoregressive scheme is. So I find it amusing that they use autoregressive spectral estimation as a triumph of the Bayesian approach, but the criterion that we use for determining the order is really a frequentist approach.
But the CAT criterion also works for vector ARs.
Oh yeah, and I'm very proud that I extended it to multiple time series, so we have a multiple time series version for determining the order of a multiple time VAR.
It also actually works for periodically correlated autoregressive processes, which periodically, no pun intended, get rediscovered in various literatures.
That's true.
Yes. Well, since you're, so you wrote a very seminal paper on quantiles and functional data analysis in JASA, and since then you've been on a crusade to to spread the word of the quantile domain. So here's your chance.
Well, I feel that elegance and utility, you can't beat the quantile domain. And when I discovered quantile, and I discovered many beautiful formulas, tables of density quantile functions, score functions, and I asked leading statisticians, how come people aren't paying attention to these formulas? They gave the typical answer, oh, we know all that. Well, where's it written down? It's folk theory. I feel that one of the unfortunate problems with statisticians, they have a way of telling people who discover interesting things, oh, we know all that. You just haven't bothered writing it down any place you can find it. But don't bother, it's kind of all known. And I feel that a reflection of the sad state of quantiles is that most people who teach quantiles not aware of the fact that there are several definitions, that they're using a definition in the class, that isn't a definition in the book, that isn't a definition in the computer program. SAS has 4 or 5 definitions, and they have no idea of what the differences and motivation of these definitions. So I feel that it's honest to say that the level of ignorance of quantiles and quartiles and medians among statisticians is very high, and they don't seem to want to sort out the ideas, although everybody, including all mathematicians, want to teach quartiles. Quartiles, introductory statistics, is widely taught in America. And yet, when you point out to people teaching it that there's this incongruity between their definition and how the bookers do it, they don't seem to be bothered.
So it has both a huge data utility, but also theoretical for...
Well, the point I was saying earlier, statistics has to move from analyzing data in terms of mean and variance, in terms of distributions. If you have a scatter diagram in the plane, an XY plane, the regression line is an estimate of the conditional mean of y given x. We should also estimate the conditional quantile of y given x. And I have very powerful methods of doing that, which are different from the so-called quantile regression approach. And what you do is you draw these contour plots of the 95 percentile and the median and the quartiles, the 5% percentile, and they're just, and incidentally, if you want to get the conditional mean, you can express the conditional mean as a linear combination of the order statistics, so you actually aren't depriving yourself of the regression function of a conditional mean by also applying the conditional quantiles. And
so you've promised to write a book on all this, is that right?
I absolutely feel that, well, I've reached the point where I'm interested in applying this, even introductory statistics. I feel that the basic facts of statistics, what makes it work, is just not well understood. For example, if you look at introductory books on statistics or people doing research in statistics, they make assumptions that seem to come out of the blue. Well, we'll assume a monotone Lockheed ratio. And what I have discovered is that there's a concept called stochastically increasing, which if you express in terms of distribution functions is decreasing in the parameter, which is kind of strange. Why do you call it increasing when the criterion is decreasing in the parameter? But if you express it in terms of the quantile functions, then it's increasing in the parameter. Now, any function which is increasing has an inverse. And I believe in the principle if you can measure it, you can interpret it. So the inverse of the quantile function of the sampling distribution turns out to be exactly what confidence intervals are estimating. Right. So there are many beautiful relationships, which I think are worth knowing because they're beautiful. And also I believe in the unjustified application of mathematical thinking to the real world. These turn out to be simple, elegant to understand, elegant to implement, applicable to real data. And so I want to, in particular, what I've said is that we wanted to teach statistics from 3 points of view. I call statistics 1, how it works, statistics 2, why it works, statistics 3, proofs. So the idea of bringing the proofs in would be the statistics 3 version, statistics 1 would be the really introductory version, and statistics 2 would be an outstanding problem of statistics education is statistics 2. What course should we design for students to follow up an introductory course? And that's called the statistics 2 problem. So I am saying that the statistics 2 problem is to teach why it works, where in statistics 1 we teach how it works.
I had left one of the people for later, and that's Fred Mosteller.
Well, Fred Mosteller had a big influence on me. He recently died. He was a truly great man. He was a founder of many programs at Harvard, and I was lucky, as I said, to have become a student at Harvard. And the very first time that Mosteller taught the math stat course at Harvard, I was a student in the course. So I have known him over many years. We've had a lovely interaction, and he was very supportive of me in my career in many ways. In particular, I was invited to be a fellow at the Center for Advanced Study in the Behavioral Sciences at Stanford, which was a significant year in my life, because of the high recommendation of Fred Mosteller. And we always enjoyed talking to each other, and he used to say, I tell everybody I taught you everything you know. That I don't mind just saying that. It's an honor to have been your student. So that's my Fred Mosteller story.
Yeah, I've heard him say that, actually. Yeah. Well, thanks. We only have a few minutes left. It's appropriate time to, what's the future for Manny Parzen?
Well, I intend to write my books on statistics 1, 2, and 3, trying to explain the basic, well, I like to say all of statistics in 45 minutes, that the basic ideas of statistics turn out to be applications of the idea of increasing functions, and that's a quantile function. At the same time, I feel that among statisticians, there's a big tendency for them to want to be scientists and not students of statistical theory. And I feel that both are necessary, that for their research and their collaboration, they should be statistical scientists. But there's an important problem of statistical education. Millions of people want to learn statistical methods, and the people who should be trying to make this knowledge available are the academic statisticians. I think the problem of academic statistics is how to provide statistics education for the millions of people who want to apply statistics. So I also feel that academic statisticians should have active seminars on the history of statistics, so they don't forget about all the important, wonderful theoretical contributions that were made in the last 50 years. So that's my recommendation. Academic statisticians, in addition to being statistical scientists, should recognize they have another job. That's unfortunate. You don't want that job. Don't become an academic statistician. They have to be concerned with statistical education, with statistical scholarship, maintaining the history of statistics, and as I said, trying to be in fact, in my career, I was successful because I was a resource for many applied people who want to learn statistics, they want to learn foundations, and they found what I wrote as very helpful in clarifying what they want to do in their practice. And I think that that's what the goal of academic statisticians should be, in addition to being statistical scientists.
Well, I'd like to thank Grace and Manny. This has been great fun. Thank you very much.